I think we can start. It's 3 o'clock Central European time, and I would like to very warmly welcome you on the session. Good afternoon, then. Good morning and evening to all of you joining us worldwide, because this is the global webinar, which is common for all the DME companies and entities. Today, we'll focus on our two main solutions in the undercuts area, which is our DME S-Core and Dura collapsible core technologies. We will cover their key benefits, and we'll also mention some customer success stories. My name is Adam Schneeberger. I'm the European Marketing Manager. I'm joining from the Czech Republic, and I will guide you through the session today. Let me quickly introduce our speakers or our team. Joining me are Jeremy Sutch, who is DME Director of Engineering. He's based in United States. Then I've got with me Joerg Voss, who is the Sales Manager for Germany. Then also we have here Ditty Thomas, who is the Global Product Design Manager based in India. I will not repeat my name, but I also have here my colleague from DME North America, Mark Zaborny, who is the Marketing Manager. He's sort of holding a ghost position today, and he's gonna be running the chat and supporting us during the Q&A sessions. The webinar will last approximately 40 to 45 minutes, and then there's gonna be enough time to cover your questions in the Q&A sessions. You are all muted during the webinar, but you can anytime type in your questions into the chat. The webinar is gonna be also recorded. And now I will hand over to Jeremy to begin. So, Jeremy.
Thank you, Adam. Thank you, everyone, for joining our webinar today. We hope you find it educational and contact DME to discuss project opportunities for collapsible core for undercut. We're going to start our presentation with talking about some of the traditional ways that undercuts are created in molding, injection molding. Most of you are probably aware of all of these, and try to use these examples as an offset or a differentiator between this technology and our collapsible core technology. So number of examples to the right there. One of the traditional ways to create an undercut is with a side core internal slider. One of the limitations with this option is that it won't do a 360-degree undercut, and it's not suitable for small diameters. Our DuraCore and S-Core products that we're going to explain throughout this presentation are capable of both. Another option is a lifter mechanism, and that cannot handle a 360-degree undercut where the Dura and the S-Core can. A more costly, complicated method that in some cases may be the best solution, but differentiates from a collapsible core is an unscrewing mechanism, whether that be electromechanical or hydraulic. This unscrewing mechanisms are very expensive, they're costly to maintain, and they typically will lead to a longer cycle time, where the collapsible core actually is better in all of those cases. Bump off undercut or forced ejection is not good for soft materials. It's potentially going to deform the part. And then a loose core type solution is not good for mass production. It really requires manual intervention. Next slide, please. Benefits of DME collapsible cores. It simplifies mold design and reduces engineering complexity. Faster and easier mold setups save valuable time. Flexible sequencing improves process control. Low maintenance ensures higher uptime and lower operating costs long term. Superior part quality with no stress marks. Greater design freedom for complex geometries. And reduced cycle time increases productivity. Next slide. Differences between the DME S-Core and the DuraCore. Very important differentiators. The S-Core is what we refer to as a dovetail type of design. And you can see, and you'll see in better detail as we go through the presentation, how that dovetail detail actually interlocks the inner and outer moving elements. And so as the mold opens and closes and moves the inner segments, basically it's driving the outer segments of the core. So it's a constant mechanical interaction between the inner and the outer cores. Through that, though, the S-Core is capable of accommodating a very wide range of shape applications and a much greater undercut, depending on the application, as we'll see as we go through the presentation here. The DuraCore is actually opposite the S-Core in how it's manufactured and how it operates. The DuraCore is a spring-type collapsible core. The inner and the outer elements, as they move, as the mold opens and closes, they actually do not come in contact with each other until the very point of full expansion. And this is very, very helpful in that it reduces wear and it extends the life of the core. And one of the other differences that is very important between S-Core and DuraCore is due to manufacturing methods of each, the DuraCore can be a more cost-effective solution depending on the actual part shape and application. And although with the S-Core, we can really achieve much more interesting geometries. But our application engineers look at every collapsible core opportunity that comes to us. We look for solutions with both DuraCore and S-Core so we can deliver the system that's going to provide the greatest value to the customer. Next slide, please. Some key differences or uniquenesses between the S-Core and the DuraCore. The S-Core is available from a very small 6mm diameter up to a rather large 400mm diameter. The DuraCore is limited from 20mm on the small side to 70 on the large side. From a footprint, from a mold real estate standpoint, as you can see, the mounting plates of the S-Core to the left there, available square or round, but they take up a little bit more real estate, whereas the DuraCore is an all cylindrical design, kind of a more traditional look of a collapsible core. The S-Core can operate with a shorter stroke or less mold movement. The DuraCore requires a little bit more movement to get full stroke. Surface contact with the part, the S-Core is 100% full contact. And the DuraCore, depending on how it's designed in the application, could be a little bit less. Under design type there, we have the S-Core listed as customized design. The DuraCore is a standard design, and that's kind of misleading in that every one of each of these cores is custom engineered for each particular customer application. When we say that the DuraCore is a standard design, we have limited it to a number of set diameters. So there are a number of different series and sizes, and we have to be able to make DuraCore work with the part with one of those standard diameters. Safety stops to protect the core and the mold, available on the S-Core and available on the DuraCore. As we talked about with the dovetail, the inner geometry of the S-Core is tapered, whereas the DuraCore is straight. Both of them offer excellent cooling efficiency. We can have an internal core that's cooled. Both eject with straight linear motion of the mold. Front insert feasibility. This has to do with actually adding some part shape at the front side with the S-core that is feasible and not feasible with the DuraCore. Undercut percentage, this is a pretty significant difference between the two. You can see the S-core, single stage S-core can do undercuts up to 13%. We offer the S-core in a two-stage, which does require an additional plate and additional mold movement, but we can go up to 23% undercut with the two-stage, where the DuraCore is only available up to a 10% undercut. And I should say that in all cases, it's going to be completely dependent, those undercut percentages, on the part geometry, the length of the undercut, and that ratio between collapse and that length. Next slide, please. And just some keys to actual mold cavity design when using a collapsible core. We've got some little drawings there that show that we want to be sure that the part is held concentric in the cavity with the collapsible core. You don't want a situation where the part detail actually can release itself as the collapsible core begins to collapse. So when we look at these designs with our application engineers, we'll look at this part of your mold design and make some recommendations to try to make sure that we don't have any problems with that. Moving on through the presentation, Joerg Voss, sales manager at DME Europe, is going to talk about the S-core specifically. Welcome, Joerg.
Yeah, thanks, Jeremy. Welcome to our webinar from my side. So what we can see here is a range of our S-cores that we have in different sizes, you can see it, and with different possibilities of percentage undercut, what we can use with these cores. So we started with maximum 13% for the single stage S-cores, and it's up to 23% undercut with our two-stage ejectors. S-cores. But it's up to the geometry how much percentage we can realize. Next slide, please. Here you can see two types of our S-cores. On the left side, you can see the 6-segment version, and on the right side, the 8-segment version. So we have possibilities to do this with 6 or 8 segments. Why we have it? Because it's up to the geometry and the complexity of the part that we will eject it or produce with these cores. So sometimes we only need 6 segments, but sometimes with more complex geometry, we have also the possibility to do this with 8 segments that we can better produce it what the part has needed. So the function is also the same, but here we have sometimes more segments for the undercut. And again, here, Jeremy explained it in the slides before, we started with 6 millimeter diameter, and it's at the moment at 400 millimeters on the diameter. So we have a big range of solutions what we can provide to you as our customers. Next slide, please. Here we can see our safety stop. So it's very important that you as a customer know this, that we have these as a patent version. So only DME can provide the solution to you as a customer. The safety stop, it means so the segments cannot touch together, because we have implemented in the cores a safety stop that we don't have any damaging during the moving process of the sliders. They cannot touch together. So it's very important for you that, as an example, also in the maintenance process, when you take the maintenance process from your tool and mounting out the S-cores from the tool, and your member of the tool shop will see how the cores will work and moving the core forward and backward. In our case, it's not possible to damage the sliders because they have a safety stop and they cannot touch. So it's very important for you to know this And it's a really good safety argument, and it can save you a lot of cost because they cannot damaging the core. Next slide, please. Here are a little bit explained the design from the retaining rings. So we started on the left side with a square version of the retaining rings. Then we have in the middle the standard one with a round square retaining rings. And on the right side, we have our rack system. And why we have these difference in the retaining ring design. So when you see the left, the retaining rings in the square version, it means you need not so much space in your tool like on the round retaining rings, what we use in the past. So this is a reason why we use a square version normally, because you need not so much space in your tool. It means the tool can be sometimes smaller. You can use sometimes a smaller machine. So it's reduction of cost for you as a customer to produce or to build your tool with our SCORs. And on the right side, you can see our rack system, why we have this also. So sometimes the distance between, in this case, it's a thread as an undercut, are so small that you cannot use a standard SCOR with a square retaining ring. So it means the spaces is not so big that you can implement this. In this version, we can use our rack system, and it's a minimum distance is 13 millimeters, but it's up to the dimension from the undercut and also from the part. And we have maximum 8 cores in a rack system that we can place. So you can see it's not so critical when you have not so much space in your tool. We have a solution for you. Next slide. So here we have also some of the versions from our SCORs. On the left side, you see standard. But standard means normal, the core looks like this. But every SCOR, what we produced for you, is a special one. So it means our designing engineers checking your design from your part and created a core for your part. It's not like we have it in the warehouse. No, it means we produced direct for your solution, the core. But in this case, standard means we have a thread what we will with the undercuts on site and what we produce with them. In the middle, you can see a custom, what we call custom versions. It seems it looks like not a thread, so it's a little bit high-end undercut. What you can see with different dimensions, diameters on the core. So it's not every time that we only can eject it a thread, so we can eject it everything what you want in the range of the percentage from the technology what the core can do. On the right side, you can see also the rectangular version. So sometimes you need it also as a square version. It's also possible to do this. And on the left side, on the bottom, you see our DLC coated version. What does it mean? So sometimes the plastic material what the customer will use from their part, it's not so easy to handle with, as an example, some filled material, PA, with glass fiber. So as a protection of the core, we will coat it the core. So the customer had the choice to have the coated complete core or some segments from the core. So it's possible to do both. And on the right side, you can see again the less footprint versions with our rack system. Next slide. So here you can see a video, a demo video with the function of the S-core and the different positions in the tool. It means in this video, we show you as a customer the different possibilities, how you can place the core in your tool with different functions. And on the fairs, we have the samples, the blue phone holders. Perhaps you have seen on the last fairs, and this is a tool and this video how the tool looks like, which one we produce the samples. So Adam, please start the video. And after the video, the colleague Ditty will take over. Thanks for joining.
No problem. I will just start it. Just please let me know if you can also hear the sound.
Not yet.
Okay. So I will quickly stop sharing and I will try to do it once again. Just a second.
And a reminder, while we're waiting for Adam to bring this back up, if you have any questions, please put them into the Q&A section. We will get back to them at the end of the presentation.
Okay. Just let me know if it's
Introducing
any
the
better now.
DME S-Core, the next generation
Yes, we can
collapsible
hear.
Yes,
core,
Adam.
offering
Perfect.
a premium undercut solutions. Let's explore the challenges in releasing part undercuts. Challenge 1, a small undercut, just 6 millimeters in diameter. The solution here is a small S-core with an interrupted thread design, engineered to release a 12.6% undercut. Challenge 2, a square undercut. By using a square S-core, we can reliably release this 6.3% undercut. Challenge 3, a large round undercut, 35 millimeters in diameter. The solution is to use a round S-core to release this undercut. Challenge 4, managing multiple undercuts within a single part. Here, we take a closer look at the innovative S-core in action. Powered by DME's new patented positive stop design. This technology eliminates any risk of collision between the folding cores during travel, ensuring smooth, damage-free operation every time. Let's take a look at the mechanisms of all the S-cores in action. Watch as each core operates in sync, working together to release complex undercuts and eject the part efficiently. First, plastic is injected into the mold, forming the part shape. Before the parting line opens, the 6 mm S-core collapses, releasing the undercut. Next, the parting line opens, causing the square S-core to collapse and retract from the part. Finally, the floating B-plate collapses the core, and the ejector pins push the part out.
Okay, so that was the video. Now going to the other slide. Ditty, I guess this is your slide, please.
Thank you. Thank you for joining this session. My name is Ditty Thomas. I am working as a global product design manager at DME. So let me, in the previous section, we discussed working principle in detail. Now let me take you through some real life examples. On this slide, we are looking at the small part with the interrupted thread. Usually, we can try bump of ejection when the diameter is more than 25 mm and the material is flexible like PP. But in this case, the material is 10% glass fiber filled nylon and the diameter is only 6 mm. So bump of ejection, it won't work here. For this kind of situation, we are using our unique product called S-core. S-core can handle the undercut up to 13%. In this example, the undercut percentage is 12.6%. So it is within the safe range of S-core. To achieve proper collapse, we are using 6-segment design on this. This type of application is very common for small threaded part where the space is limited. Finally, this product is already working well at the customer side. Can you come to the next slide? Here you can see standard threaded component. The undercut percentage is only 6.8%. Again, we are using 6-segment system. By using S-core for standard thread, you can save a lot of cost in the production. This is mainly because of the cycle time reduced and the process is optimized. Now you just imagine if you have a long threaded component, you need to use unscrewing. which take more time for ejection and also for screw it back. But with the S core, it's matter of seconds. The core can collapse during the mold opening and return back during the mold closing. So you can clearly see how much time is saved. This is very typical and stable application, and it is worked well in the production. You can come to next slide. Normally we think a collapsible core is always in round shape, but it is not always like that. In this case, the component is square or rectangular in shape. So we adapt the design according to the shape. This design works well, square or rectangular in shapes. To get a proper collapse, here we are using 8-segment design. The rectangular collapsible core is a game changer. It can handle the complex undercut easily and make the production simple. You can come to next slide. This slide is very important from the design point of view. If your product is very small and looking simple like a core and cavity design, there is a chance that the part may stick on the collapsible core. This is happened because there is no proper holding feature keep on the part at the center of the collapsible core during the ejection. And also, if the part line is placed at the radius area, the part may slip during the ejection. So we recommend adding a locking feature to hold the part properly. And proper part line selection will improve the stability and avoid defect. This is very important point for the reliable production. So next, Mr. Yoga will continue.
Yeah, thanks, Ditty. So what we see here is our two-stage S-core. So it's the newest innovation what we have in the S-core technology. So we started in the presentation with inform you about the percentage for undercut. So again, with this technology, we can maximum ejected 23% of undercuts, but it's up to the application. Is it reachable or not? And you can see here the package of the retaining rings. So we have two packages of it. Next slide, please, so we can better explain it. So here on the left side, sorry, on the left side, you have the ready to mold version from it. So it means you have the two packages of the location rigs, and then in the middle, the first stage collapsed. So it means it's similar like a two-stage ejector. So it means the segments don't move together like from the standard core. So it's moving step by step. It means in the first stage, the smaller segments moving inside to give the space for the bigger one that they can collapse a little more because we have a higher percentage of undercut that we can eject it. So it means they need more space as in the standard version. And this is the reason why on the first step, we have the smaller sliders that moving, and then they give the space for the bigger one to move forward. And this is the reason why we have the second stage. So on the next slide, we have also a video animation that you can see on this animation how it works, and to explain a little bit better how it works in the tool, you can see also a tool and also some ledge locks as a complete system what we also sell for the S-cores. That's from my side. Thank you for joining this webinar, and then Jeremy will take over.
Okay, I'm starting the video.
Introducing the two-stage S-core, revolutionary two-stage collapsible core, mastering undercuts beyond 13%. Let's explore the challenges in releasing large undercuts. This small bottle part has an internal undercut of 16.2%, far exceeding the standard 13% limit that conventional single-stage collapsible cores can handle. Let's break down how the two-stage S-core operates. In the first stage, the core begins its partial collapse, releasing the primary section of the undercut. Next, in the second stage, the core completes its full collapse, allowing for the complete release of larger and deeper undercuts. Now, let's see the mold base operation in action. First, the first stage plates move, initiating the partial collapse of the core. Next, the second stage plates move, completing the core's full collapse. Finally, the stripper plate ejects the part from the mold, completing the cycle with precision and efficiency. This section view highlights the movements of the various segments within the collapsible core, showing how each component works together to achieve the core's function. Let's take a closer look at the GTSL latch lock. It functions as a guide bar on the outside and a three-stage latch lock on the inside, controlling the three stages of plate movement while guiding the moving plates. During the first stage, the latch bar holds all three plates together for the initial stroke. Next, the latch bar disengages from one plate, holding the remaining two plates together as they move to complete the second stroke. Finally, the stripper plate is released, allowing it to move independently and eject the part. Here, we see a full section view of the mold base, showcasing how the two-stage S-core is mounted across multiple plates. Each plate moves in a controlled sequence, with a designated stroke for each stage.
Okay, so next slide, there's one more Ditty for you to cover. Thank you.
Yeah, fine. Thank you. Yeah, again, I will just explain the product in detail. This part is like a cosmetic container. So the surface finish and visual appearance are very important. Now coming to the technical point, in this design, the undercut percentage is 16.2%. This is higher than the normal limit. Usually, single stage S-core can handle only around 13 to 14%. So in this case, a single stage S-core, it won't work. That's why we are using two-stage S-core. This design provides additional collapsible movement, and it can handle the undercut up to 23%. So we can manage this design without changing the product. This is very effective solution for larger undercuts. Can come to next slide. Yeah, from here, Mr. Jeremy will continue.
Thank you, Joerg and Ditty. Moving on into a little bit of detail about the DuraCore product. We go to the next slide, Adam. So, as noted in the beginning of the presentation, the DuraCore is a spring-type collapsible core. There are no actual springs. The metal is actually worked to actually create spring action of the inner and the outer elements. The DuraCore is available in an 8-segment, 10, 12, and 16 segment designs. Again, how many segments our application engineers choose to use is going to be dependent on the part geometry and the complexity. And as you would consider, as we increase the number of segments, the cost of the core does increase due to the complexity of the manufacturing process. Next slide, please. The DuraCore safety ring is in place and is there to ensure that the core completely collapses with the plate movement. It prevents interference between the segments in the molded component, and it maintains proper ejection sequence and timing. And the safety ring as a separate component is only required for the DuraCore smaller than 40 millimeter. DuraCore 40 millimeter and larger, we actually incorporate safety ring type geometry in the inner and outer elements, so there's not an additional component. Next slide. I believe we have another video to show the DuraCore in action.
Yes, we do, Jeremy. Just starting now.
Premium yet cost-effective solution for parts with internal threads and undercuts. Introducing the next generation of spring collapsible core, DuraCore, for internal threads and undercuts. Key features are avoid segments contact during motion, easy cleaning and maintenance, short safety ring, improved cooling, reduce mold base stack height. Key attributes are sequential opening, two-piece design, shorter safety ring, use of straight core pin, reduced collapsible core length. Benefits of two-piece design, effortless disassembly for easy inspection and cleaning with rapid, secure reassembly to minimize production downtime. Enhanced safety achieved through a shorter safety ring mounted securely on a safe plate. Optimize manufacturing and cooling efficiency with a straight core pin, leading to improved overall performance. Realize space-saving advantages with a reduced collapsible core length, effectively minimizing the mold base stack height. The space-efficient design accommodates more cavities, maximizing production output per cycle and boosting overall efficiency. DuraCores are available in round head or flush head forms. DuraCore advantages. During the mold closing phase, the large segments smoothly pave the way, allowing the small segments to follow suit. Small segments follow the large segments without contact. This ensures no additional load on the small segments during the mold closing phase. Large and small segments move without touching each other. This breakthrough minimizes wear and tear, enhancing durability of the DuraCore. Thank you.
Thanks, Jeremy. Again, I am going to explain about the real-life example. In the previous slide, we talked about cosmetic bottle, how we can incorporate with the two-stage score. Now I am going to talk about the cosmetic enclosure. So here also the surface finish is very important. So now coming into the technical point, the undercut percentage is 9.1%. And you can see another advantage, it can handle small nearby profile easy. Also, cooling can be provided very close to the part. So the heat transfer is better and this gives faster cooling and reduce the cycle time. So overall, the DuraCore is simple, effective and reliable solution for this application. We can come to next slide. Now in this slide, you can see DuraCore application, the undercut percentage, again it is 9.1%. So it is within the feasible range. The main advantage here is the cooling efficiency. You can see right side at the bottom. The cooling lines are inside of center core. So heat is removed quickly and directly. Also, cooling is very close to the molding area that gives faster cooling and reduce the cycle time. This design also avoid heat concentration areas. So the cooling become more uniform. Finally, we get a stable production and good part quality. Overall, DuraCore gives simple design, better cooling, and higher productivity. We can come to next slide. This is another one DuraCore application. Here the undercut a little bit more, it is around 10.9%. The key advantage here it is the center core concept. As you can see, the center core cover most of the internal profile that give a good support and stability during the molding. And also cooling can be placed very close to the core surface. So the heat removal is quick and direct, so the cooling become more uniform. This improve the cooling efficiency and give stable cycle time that give a consistent part quality. Overall, this design give better coverage and better cooling and better productivity. So, Adam, I think we covered. We can just move to do the question and answer section.
Yes. Thank you, Ditty. Indeed, it was the part of the official slide presentation, let's say. We've managed in 40 minutes exactly. And now we can jump straight to the Q&A. As I've mentioned at the beginning, you can enter your questions to the chat, and we will try to cover those. I can already see the first question, which has been sent to us by Stephanie. So I'm gonna read it loud. What kind of maintenance can we expect compared to conventional unscrewing mechanism? Jeremy, maybe, or Ditty?
Sure. So both the S-core and the DuraCore are expected to be dismantled during standard mold preventative maintenance periods. And both cores do need to be greased during that preventative maintenance, but that's it, right? So if you were to look at a traditional unscrewing device, you've got a lot more moving components, other wear items that need to be replaced. So really, a small tube of grease for Dura or S-core, versus more complex preventative maintenance on an unscrewing system, there's definitely money to be saved over the life of tool.
Thank you. Now I'm gonna read also some other question from Paul, what I can see. Can S-core or DuraCore be integrated into existing mold design, or are they mainly suited for new tool builds?
With a minor modification on the mold base, we can incorporate both DuraCore and S-core. There will be a slight retrofitting is required.
Okay. Then third questions, what I read here is from Dunya. And what kind of cost savings have customers typically achieved when switching to S-core? So this one is very interesting because everyone is really keen on cost saving. Maybe Jeremy?
I'm sorry, Adam, I was trying to find that question in the chat. Could you repeat that, please?
Sure. What kind of cost savings have customers typically achieved when switching to S-core?
So that's kind of a question that's hard to quantify. Switching to S-core, from a different undercut relief mechanism of sorts, it's too general of a question to answer. What I would say is that if S-core, DuraCore are designed for a particular part application, that it's going to be done as economically as possible. And again, we spoke briefly about maintenance, very low maintenance, upfront cost. It's essentially the same as a complex, unscrewing system, but long-term, much less expensive to maintain. So unfortunately, I cannot quantify that, an answer to that question.
No worries. Thank you.
Adam, in my previous session, I just explained about the working principle. Usually for the S-core, usually for the unscrewing device, there is a need of separate time to screw it back and ejection. But in S-core, it is can be a parallel application. While the mold opening, the cold will get a collapse, and while the mold closing, it will come to the original position. So you can easily calculate the time. I don't need any additional time for the unscrewing application.
Okay. And I can see here one more question. I'm just gonna read it again. How does S-Core perform across different materials? Are there any limitations for filled materials or soft polymers?
Usually the soft material we can try with the normal material. Usually we are using 1.2344 as the material grade. So for the unfilled material, we can use that. For the filled material, like a GF 30 to 50% of GF filled material, we are recommended to go with the DLC coating. That will give a better output and reduce the wear.
Okay.
Hey, Adam, we do have some other questions in the Q&A section. One question we do have is about transparent parts. What about witness lines from the core when you're making transparent parts?
Usually that width lines need to be present. That in dimensional ways, I can explain that it can be plus or minus 10 microns. So it will be visible for the transparent material.
Okay, and we have a question about the safety stop feature. Is that something that is new in the S-Core, or has that always been around?
That's always been a part of its design.
Okay. What also are the expected service lives of the cores?
Generally, we say that, again, depending on the application, and there's a lot of a lot of influence on how well the mold and the collapsible cores are taken care of. We do expect up to 1 million cycles for each of the S-Core and the DuraCore.
Okay, and then again, everybody, if you have questions, please put them in the chats. We have another question here is, what is the rough cost comparison with servo-driven unscrewing molds?
Again, I would say, generally speaking, an upfront cost, there probably can be some savings using collapsible core. Certainly, it's a simpler design, simpler mold design. Long term, over the life of the mold, the collapsible core is going to be much more cost effective to maintain than an unscrewing system.
Absolutely. Then how does this apply to high cavitation screw closure molds with tight pitch spacing?
Yes, as we explained in the slide, we have a separate rack mechanism. The lowest pitches of the cavity, it can be 30 millimeter.
Okay, and then for medical parts, can you run greaseless?
We don't recommend operating the DuraCore or the S-Core without any grease, although it is a very light application of grease, very light. And DME offers several high-performance grease solutions that won't break down over time, which allows for longer preventive maintenance cycles. But we do recommend that the segments are greased.
Okay, and
Perfect.
Perfect. If anybody has any other questions, the panel is open. Adam, do you see any other questions on your side? I'm looking at mine. I think we're.
No, I think we are pretty much done. If they're gonna be, we are gonna cover them afterwards. Also, I would like to mention that we are gonna share some important contacts. I'm sure Mark already shared in the chat. We'll send you the contacts for our engineering departments or special projects department, with also some links for the S-Core and DuraCore marketing literature, some leaflets and brochures, so you can read through to check more details. And as mentioned, in case of any quote needment, then please let us know, and we are going to be quite helpful to assist. Ditty and his team is ready. So I think, Mark, that's it. We are gonna
one more.
stay connected. Yeah, we have one more. Okay.
Yeah, we got one more question here. Do we offer repair services if a core is damaged?
It is very possible. And certainly we could always, if an inner and outer element is damaged, we could reproduce just that, that single element rather than the entire collapsible core. So definitely repair is a possibility for both the S core and the Dura core.
Perfect. And then there was a comment. Yes, we can share the presentation after if you want to share this with other people in your office, things like that. Absolutely. So we will send that out probably within a week or so on there. So last call for questions for our panel here. And if not, Adam, I don't know if you see any other.
Okay, then thanks everyone for joining. And Mark, maybe you can also invite the audience for the next webinar, which you are working on, because we are currently doing like a series of webinars.
Oh,
so maybe
absolutely.
You can...
Yeah, so we will be having another webinar on May 18th. It's a servo mold webinar for the North American customers over here. So more information will be going out. Keep an eye out there. And the invites that we had earlier for this presentation, we also included a servo mold. So if you want to go back and re-register, you definitely welcome you to do that. If not, I'm sure I'll be reaching out to you as well. Again, so keep an eye in your inbox for that. Also, if you haven't already, please follow us on LinkedIn. You'll find all the latest and greatest news for both DME Europe and North America at both of our pages. Link them both of us, follow us both, just to get the latest and greatest of what we are having.
Perfect. And I think this is the very end. So thank you very much for joining, and we are going to be having a next one, so stay tuned. Thank you. Bye-bye.